We're streaming this live. So Eric, this is Eric going out to the world with us as guinea pigs.
Was that we're screaming this live?
Screening.
Screaming.
Screening.
Screaming this live.
Are we on?
We are on.
We are on. Okay, let's roll.
First time.
Let's roll the show there. Okay, we're counting on you, Eric. Well, welcome everybody to the November meeting of the Ottawa Centre RASC. I'm glad you could all make it out. And are you getting pumped? Ice on, right? Anybody seen ice on yet? Yeah? Oh, yeah. I see a few hands going up. Excellent. All right. Well, folks, we're like, we're what?
I have none. I won't tell you why.
Yeah, okay. We can discuss that later. We're 4 weeks away. 4 weeks away from its closest approach there, so I'm not going to steal Tim's thunder. He's got an excellent program for us tonight. We've got a really good show actually for you tonight. A lot of good talks, and as I mentioned, Eric is beaming us out to the world there. So be on your best behavior, speakers. You know I'm looking at you, eh, Tim? Right? we. All right, so we've got Gary up first. He's going to talk to us about Ottawa skies, what's happening in the sky in over our gracious city here. Mr. Cole is going to give us an excellent presentation on Comet ISON, very timely, especially with it making its close run in at the sun in just 4 weeks. Jonathan is going to give us a report on a rather interesting book that's out. I'll let him deal with that. Al's going to give us our 10-minute astronomy update and also going to talk to us about nominations for positions at the Centre for the coming year. Then we'll have our break. We'll have some good observations in. And then Simon is going to talk to us about the Grail mission out to the moon there. So some interesting graphics and always entertaining with you, Simon. And then Jim Thompson will give us an interesting peek. I reviewed the slides for this when Chris and I were putting together the show, and I think you might find this really interesting, especially for those of you that are, like me, a little bit older and remember browsing astronomy books from the 70s and 80s compared to the imagery that we have on deck nowadays. Some really interesting comparisons there with world-class astronomy and observatory facilities of the 80s vis-a-vis what an amateur can do with off-the-shelf hardware nowadays there. So hopefully we won't, we've got a pretty packed program tonight, so hopefully we'll have time to fit all that in there. But yeah, looking forward to that there. So next slide, please there, Chris. We wanted to take a moment to thank new members for joining our group there. We have 10 new members, excuse me, 10 new members in the list, absolutely. And so welcome. I'm glad you found your way down here, and I think you'll enjoy your membership. There's a lot of people here that like to talk astronomy and gear and all the rest of it there, so I hope you enjoy your time with us. And hopefully we'll get you up here sometime to give us some talks as well. Members in the news. We have one member in the news. I wonder who that might be from. What do you think? Head scratcher, right?
I don't know.
Another excellent shot from Pierre Martin. Beautiful work there, actually. I love the composition of it there with the clouds and the foreground there. So nice work, Pierre. All right, and I think without further ado, Mr. President, come and join us. There's your pointer.
Thank you, sir.
You're more than welcome.
Well, welcome everyone in the audience, and welcome everyone streaming for the first time. It's the inaugural flagship event for sure. Haven't logged on yet, but whoever is watching, I hope you will enjoy us for the first Friday of each month. And I'll be getting on the chat room after this, the astronomy chat room, folks, and answer questions for our first-time viewers. But it's lucky that we can see this live. Eric, when is the recorded version will be on?
As soon as the broadcast is over.
Okay, then it gets recorded?
It's sent to a server on Ustream, and you can click on it right there.
Okay, great. But if you live within, start within 20 light years, you'll see it 20 years from now. Sorry.
That's right.
Next slide, please. So here we have Venus. Venus hasn't had a very good apparition because it's very low on the ecliptic. The ecliptic runs right through Sagittarius, and in fact, it's at its greatest elongation on the first, pretty well today. So it's the furthest from the sun, 47 degrees, but it doesn't get any higher. But other trends, when Venus will come around, it will get higher in the sky as it gets higher in the ecliptic. The great show begins now because as Venus is moving between the Earth and the Sun, it gets closer to us, gets larger, then we get phase structure. So those with telescopes, within the next couple of weeks, that's the time to look at Venus for sure. Next slide, please. On the 3rd, there's going to be a hybrid solar eclipse. That's because of the trajectory and geometry of the Earth, curvature of the Earth and geometry of the path. Some places on Earth, mostly around Africa, will see a total eclipse, while others will see an annular eclipse. And next slide, please. We are very lucky, hopefully on Sunday morning, that we get to see at sunrise just the very end of the eclipse. So those with safe solar telescopes, do not use your eyes even though it's low. Try for the eclipse and hope we'll get some shots for next month. So it's Sunday morning on the 3rd at sunrise. And it's great because on Saturday night, you'll be setting your clocks 1 hour back. So who doesn't want to wake up 7 or 6:30 on Sunday morning? Okay, next slide. There'll be no excuse. We have 2 comets in the sky. We're going to hear more about ISON later on. But comet Linear X1, 2012 Linear X1, has gone through an outburst. It's gained about 5.5 magnitudes overnight, literally overnight. So it's seen in the morning sky. It's still around 8th magnitude, but they think it'll come to about 6th by the time it'll be at its brightest. But it might break apart and have more material come out of it, so let's hope it brightens again. But it's great again to see 2 comets really close together, almost in tandem. Next slide, please. And on the night of the 17th/morning of the 18th, we have the Leonid meteor showers, hence the kids. The Leonids means the kids of Leo. So it's a very minor shower compared to the storm we had back in 2003, 2001, where literally hundreds per hour. In fact, a couple of thousand per hour. So the radiant will be over here, but unfortunately, the rates will be 15 per hour, and that is the night of the full moon, so that the numbers will be even lower, maybe like 2. But you never know, you might still get some bright ones. Try it. Next slide, please. And yeah, Comet Ison. So we'll just, this is a Comet Linear that's gone through outburst. Yeah, doesn't really have a tail, but anyway, try it. It's binoculars apparently. I haven't tried it yet in the morning, but it is a binocular object. Next slide. And like I said, time to fall back, 1 hour, which is good. We gave them 1 hour of sleep. For most, and again, people streaming, for most provinces in Canada, you do this. I think Saskatoon does not move their clocks back and forth. So this is the weekend for sure. And next slide. And here's the usual lunar data for the various phases. Beaver moon, again, I just call them. I don't make them up. And that's it for the month. We'll see you in 5 weeks in June. Have a good month, good observations. And hey?
In June, you'll see us?
June, sorry, in December. I plan to sleep for about 6 months. I'm so tired. I really plan to sleep, yes. So in December, we'll see you in 5 weeks. Okay? Have a good month. Thanks.
Thank you, Gary. All right. Mr. Cole is going to talk to us about ISON. Take it away. There you go.
Okay, greetings, folks. Here we have a really nice picture of Comet Ison up near Regulus, taken in early October. This was discovered by a couple of Russian astronomers, Nevsky and something. All right, Novichonok. For whatever reason, they've labeled this ISON, the International Scientific Observation Network. Why it wasn't named after the discoverers, I don't know. This is a kind of interesting comet from a couple of reasons. And of course, one of the things is it's been ridiculously hyped. Fortunately, not as badly as I'd feared, but it's still a bit of hype. Here is a lovely photograph from the Hubble Space Telescope, which really shows you a lot about this comet. It's got a very nicely formed nucleus. There does not appear, and from everything I've been able to see, nobody's observed 2 separate tails, a dust tail and a plasma tail. So we really don't have any word at all about its rotation or its sense of rotation, and we'll mention it. I'll explain why that makes a difference in a little bit. Now, this is a sun-grazing comet, and a big, heavy-duty sun grazer at that. well, heavy-duty sun grazer. It's actually a small comet. It's only about 5 kilometers across. Now, this is not one of the Kreutz sun grazer family. Those are all seem to have come from a single large comet. This is an Oort cloud object, and it's barely hyperbolic, so it's almost a parabolic. Almost a parabolic comet. So this is a nice remnant of the solar system's formation. And interestingly enough, we had a long lead time on this. It was discovered quite a while ago, which is unusual for sun grazers. So this has been a very heavily observed one. And regardless what happens from our amateur standpoint, from a professional standpoint, this is a very interesting comet. Now, there's a light curve here. I just saw last night a light curve done a few days later. This was done on the 23rd of October, and there's one that came out just a few nights ago, and it hasn't changed much, so I didn't bother updating the presentation. The peak there is an artifact of the model that they're using. All it indicates is that this is at its brightest point. There's actually a pole in the model where it goes to infinity, and it's a mathematical artifact. Now, the red dots are showing you actual observations, and this is a model that JPL has fit using that data. This is, and they make this very clear, this is by no means a reference or a standard to be achieved. This is a stock model, and they fit the light curve to it. The big question for us is going to be perihelion. Now, here we have a nice little view of the comet approaching perihelion. Right there from the underside, we've got ice on, and it's showing up here on the display. This is sweeping from the ecliptic south up past the ecliptic north. And here I've got the Starry Night rendering showing perihelion, and yeah, that is the tail that Starry Night draws on, and no, it's not realistic. It's whatever they calculate, and again, at perihelion, a lot of the models go kind of wonky, so I would take it as pretty more than really useful. You can see it's a very close perihelion, and in fact, I had to fudge this a bit. I had to get a really weird angle so we could see any variation at all. Perihelion distance on this is barely over 1% of an astronomical unit. So we're looking at about 1.8 million kilometers from the center of the sun. So we're looking at barely a million clicks over the photosphere. Now, the Roche limit for typical comets is about 2.4 million kilometers. And I'll mention Roche limit in a bit. But basically, this is suggesting that this comet has a very good chance of breaking up on its perihelion pass. Now, comet breakups, very, very common things, not always from being within the Roche limit. Here we have comet, forget it, SW3. I'm not even going to try to embarrass myself with that one. Now, that is a periodic comet, period of about 5 1/3 years, and it started breaking up in 1995. And here we have some of the cluster. It's basically right now comet bits in formation, more than a single comet. And as of the last perihelion pass, it was up to at least 66 known objects flying in formation, very much like a B-52, which has been described as a bunch of 50-year-old spare parts flying in formation, but that has nothing to do with this. Anyway, never mind. Now, Roche limit, because that's what gets described a lot. Up here we have a little picture of the Roche limit. This is basically a highly idealized notion of when tidal forces are going to break a body up. So basically, once you get inside the Roche limit, the satellite is going to deform and break apart. And this is from work done by this fellow, an astronomer and mathematician named, strangely enough, Edouard Roche, who came up with the first calculations. Now, these are not trivial calculations. I took a look at the calculations and how it was derived, and after I finished having several, screaming fits and my brain hurt horribly, I decided I would accept what Monsieur Roche has done and simply read it. It's some interesting results from his work. Interestingly enough, the limit is based not at all on math, on math. It's math. Yes, my math has gone up immensely after Halloween. Wrong math. It doesn't have anything to do with mass, but it's the primary radius and density and the satellite's density. There are two basic models that he derived, and these are what were known as liquid and rigid models. Now, the thing with the Roche limit, this is the distance from a primary at which the secondary will break up under tidal interaction. But there's a huge mass of assumptions behind it to try and make the solution of the equations possible, particularly back 200 years ago. Basically, the Roche limit applies to a body that has no intrinsic structural integrity. In other words, it's a pile of rubble held together by self-gravitation. Now, obviously, you can see there's a big problem with that already, because almost anything is going to have some degree of cohesion from, frozen bits of ice or cementing or who knows what. The Roche model does not look at that at all. The rigid model basically assumes that the object is going to be roughly spheroidal until it completely ruptures and dissociates. Obviously, a highly idealized notion right there. The liquid model accepts a certain degree of deformation. Again, I took a look at the equation and came to the conclusion that I really had no idea how much deformation it would take, but basically it does try to handle deformation, and that gives us a model that's more appropriate for things like comets. But what's happening here is the tides are starting to rip the objects apart. Now, the big thing to remember is, as I mentioned earlier, just mentioned now, the Roche limit applies to objects with no intrinsic structural strength. So, for example, even though everything in low Earth orbit is well within Earth's Roche limit, which is about 6,500 kilometers, we don't see things like the space station being ripped apart by tides. You can't do that with planetary bodies and even large stellar bodies. I don't think anything short of a neutron star can really rip up things like a piece of metal. But you will notice this effect in that there were some pictures done years ago when they're changing some solar panels on Mir. Sorry, not Mir, ISS in the early days. And they simply unbolted the solar panels and the panels drift away. And a lot of people assumed you had to put rocket motors. No, you didn't. You cut them loose and off they go. And this is, in fact, a Roche limit thing. You're well inside the Roche limit. The tides are actually separating the stuff. And this is why we could get away with doing things like blowing up explosive bolts and tossing off housings and stuff in the early days. It basically cleared away so fast that we didn't have to worry about it. The guys that came 20 years later had to worry about it, but at the time it wasn't a big problem. What I wanted to do is take a quick look at tides, because this is the whole crux of the Roche limit. And tides, for all that we're familiar with them from the beach and whatnot, are kind of a counterintuitive thing. Effectively, we're looking at variations in gravity. And, everybody here is well aware we're looking at a 1 over r squared relationship for gravity, so it drops off fairly quickly. So if we take a look at a body, and I've simply drawn it with its long axis radial just for convenience, we have a body closest to the primary. That's going to have the greatest gravitational attraction. The center, less gravitational attraction. The point out here, less gravitational attraction. So already we're getting different forces in there. There's already a tendency to pull the body into a bit of an elongated shape. Now, if we're going to look only at the differences, because we're interested in what's going to happen to the body under the variation, the simplest way to do that is to subtract the common force. In other words, the force as if this were a gravitational point, the force that you get out of just applying Newton's laws. So I animated the subtraction here. And as we subtract it, you can see at some point, the outermost point goes to 0. We still haven't completely neutralized the center force, and we end up with a residual that's outward. So we have the residuals, we have a little bit inward, a little bit outward. And these tidal forces actually change by the cube, by the inverse cube. So these drop off rapidly, and they also pile up rapidly. So as you come close to a primary, the tidal forces increase at a tremendous degree, and this is partly what's happening behind the whole Roche limit approach thing. This, most people find very counterintuitive. Let's see if I get this straight. I got a force attracting it inward, and it made the outside go out. Hello? What? Yeah, it's very, very counterintuitive. I've seen a couple of ways to try and hand wave around it. One that I remember seeing as a student back when I actually had hair was think of the innermost piece sort of pulling ahead of the outermost piece and it lagging behind. Now, I have trouble with that, but some people seem to find that useful. I find a better way to look at it is to consider what happens from an orbital mechanics standpoint. So here we've got the body that the Roche limit calculation really works for, which is a bundle of particles held together by self-gravitation without anything like cementing or anything like that. So let's pick 3 particles here. We have a vertical line here to the primary, and the particle on the inside, I've just made these big enough to put arrows on it. Doesn't really matter. We have our 3 test particles here. The innermost one is going to have the greatest orbital velocity. And I do say velocity this time instead of speed, because we'll see in a second that does matter. So if we ignore that we have this body here, we're inside the Roche limit, it's being disassembled, each part is now going to take off on its own individual path. So if we just animate our model ahead a little bit, after a short period of time, we notice that the innermost one moves a lot down and to the right, and the uppermost one much less so. And by the time we do it again, we're really starting to see the dispersion. And if we animated this for a full orbit, we'd find that they've gone a tremendous distance away. Now, if you're an observer here in the middle, you're going to see this one pulling off this direction, and you're going to see this one pulling off this direction. Not too hard to imagine in your head that there's a force doing it. It's a fictitious force like centrifugal force, but it is there, and it has the same mathematical treatment as a real force. But this is what's happening when the tides are starting to pull and stretch things apart. Here's the classic example of something that's gone through the Roche limit, and this is the standard, what everybody uses, Shoemaker-Levy 9, ripped to shreds as it went really, really close to Jupiter, and formed this incredible stream of pearls, and came back 2 years later to do some massive impacts into Jupiter, which a few of us got to see here. So the big question that's going to ask us is what happens to comet Ison at perihelion? This is the real question that everybody's asking. There's a lot of people who are already saying, well, it's doomed. It's going to tear itself to shreds. There are a bunch more that are saying, nope, its demise is, it's been vastly overstated. It's going to do just great. Anybody who's talking about comet of the century, as I think we noticed from the light curve earlier, well, for one thing, it's pretty presumptuous to say comet of the century when we've got 87 years left of the century. So I'm not going to call it that. But I think it probably indicates that it isn't even the comet of the century. We've had nicer comets. So I see 3 possibilities. It comes through with minimal effects, the nucleus ruptures, and we get a nice little dust cloud, and the nucleus just disintegrates. Well, I think the first one, forget it. It's so close, something is going to happen to that puppy. This leaves us with these 2 possibilities, and from everything I've been able to see, at this point, it's a toss-up. I was firmly expecting we'd have a better sense by now, but from everything I've been able to gather, we don't. We simply don't have good data on this. We're probably going to have to wait right until the last second. Or, days maybe, or maybe we'll just have to wait and see what comes out from perihelion. We'll just have to find out. If if Canada 2 happens, we get a nice rupture, we stretched things apart, we've ripped it a little bit, and we release a ton of dust and gas, well, we could have a very nice comet. Some of the snazziest comets around have actually had big post-perihelion brightenings. Comet West, the one that everybody ignored because they got burned on Kohoutek, and Comet Lovejoy, which the dratted Australians thumb their noses at because we didn't get to see it. They are always getting all the good comets lately. You notice that? The Aussies are getting the good comets, and we're not. What did they do? Anyway, never mind. And then if the nucleus disintegrates, well, bummer. Basically, we end up with this huge total disintegration, and we have a comet shattering kaboom. And basically, we're not going to get much. So these are our possibilities. We have a nice, pretty comet, or we got nothing. And yeah, this is Comet Lovejoy, and in fact, it's actually 2 crops of the same picture. I put in a little poetic license when I knew we were streaming, so it would look real pretty. But at any rate, never mind. So let's take a look at where this puppy's going to be in the sky. As Gary had already mentioned, it's a morning object. Here we have the path before perihelion. Here we have the path after perihelion. This is all pre-dawn, and maybe a little bit after dawn, but I doubt it. This gap here, when we aren't able to see it, basically I pulled this out of some starry night simulations. Your mileage may vary. It's probably not crazy, but is it exact? No, probably not. It's going to depend on how high you are, how dark it is when you observed. But basically, from late November to early December, it's basically going to not be terribly visible. After perihelion, this is its path. Is that path going to be correct? Probably not too far off. The real question is what's going to be moving on that path. So my suggestion is let's try to image the puppy before perihelion, when we know we've got something to look at. And I guess Paul's got some pictures, right? You got some? Yeah, good. So, we know we got it now. It's not the comet of the century. It's actually, these are the numbers I got from Starry Night, which is using the Minor Planet Center calculations, the standard formulas. So again, it's a wet finger. This is totally back of the envelope calculation. But this is kind of roughly what we're going to look at. These, don't forget, are integrated magnitudes. And what we're looking at is something that's spread over a fair chunk of sky. So it's not going to even be as bright as this. Rule of thumb that I've been told is anything above 4th magnitude for a comet, assume that it's going to be a binocular object. A little bit of fiddling. It looked like probably mid-November would probably be a reasonable time to find it at a decent hour in the morning and not terribly bright, not terribly bright in the sky. And nothing terribly good for a signpost, but we've got Coma Berenices and Porrima, and we can set up with Spica to give us a bit of a twig onto it. The moon is going to play hob with it as the month wears on because we're getting into a heavy waxing moon. And this is partly why I took a look at the 10th as a reasonable prospect, because the moon will be setting considerably before dawn. Now, I used Sky Tools exposure calculator to try and get a sense of what we were going to do. On the basis of the Starry Night simulations, I took a look at a few likely dates, went back and forth to look for numbers here. This blue line here is a quality index. Now, Greg Crinklaw, who's the writer of this, has his own algorithm for working this out. He's worked with a lot of people on it. He takes a lot of pride in it. How accurate it is, I honestly don't know. I have faith in Crinklaw, so I don't think it's nuts. Whether it's accurate, people can argue about that forever, but it's probably pretty reasonable. I plugged in my backyard, so fairly light polluted, a 6-inch telescope, and a very modest camera. Not an SLR, but basically a little webcam type camera. And what we came up with was November 10th as being your best crack at getting a reasonable image just before dawn. I think I get a sense of what he's doing here. He's looking for a point where the moon has set and where the comet is fairly near 30 degrees air mass 1, when we've got the best chance of getting a nice undistorted image. And his calculation is showing 45 1-minute exposures to get a decent signal-to-noise ratio. Again, your mileage is going to vary, but at least it gives you a sense. Here we've got the sky and telescope image for after perihelion. They're saying brightest when lowest, but again, don't forget, this is assuming that not much happened during perihelion passage. The positions are going to be right, but what's there is another question. But at any rate, let's take a look at it mid-December. Again, we've got, now that we're off nighttime wasting time, or stupid time, Alberta has it right, don't muck with it. Hawaii has it right, don't muck with it and have nice weather anyway. Anyway, never mind. Basically, again, I did the same Starry Night trick. Now we're up near Corona Borealis, so we've got a really nice signpost, and we're down near Hercules' breastplate, so this should be fairly easy to track down afterwards, he said confidently. For a guy that hasn't actually seen Comet Ison, that's kind of, oh well, never mind. And again, I did the same shtick, checked magnitudes, and here's what we come up with. December 8th, reasonably bright. I picked December 13th as a reasonable time because this is really, really low and you only have a very short time before sunrise to get it. Now remember, these are the best estimates made before perihelion. And it's a massive crapshoot at this point. We just don't know. But even with the best guesstimates we've got, we're barely binocular. So comet of the century, no. Nice comet? Yeah, maybe. We'll see. Fascinating comet from a scientific standpoint? Absolutely. This is probably one of the best studied sun grazers yet. So the stuff that's going to come out of this is incredible from a science standpoint. We just have to see whether it's a pretty show. Same deal here. The moon is turning into be a massive pain in the patoot. It's just going to be very high and very bright, and that's going to be limiting our available imaging time. Did the same trick here with Sky Tools. Came up with December 13th, just around sunrise, as your best crack at getting a reasonable picture. Again, remember, this is a whole set of assumptions piled on top of other assumptions. Your mileage can vary. I certainly wouldn't say, well, yeah, Tim said the 13th. I'm not going to bother going out until then. Yeah, well, if you do that, remember I warned you, okay? So, don't trust me. Go check it out yourself. But this probably gives you some sense of what you're looking at. 35 one-minute exposures. Again, this is assuming the comet hasn't changed to any great degree. It's gonna change. How much? We just don't know. Now, Paul put together a few suggestions here on imaging comet ISON. I'll defer to Paul. My astrophotography is, so-so. I would not claim to be very good at it. I have fun with it. Paul does great astrophotography, so I would take this stuff to heart. What he's suggesting, do it. Now, he's suggesting that comet Pan-STARRS would not be as bright as ISON. I don't know if that's... What do you figure now from seeing it, Paul? Kind of iffy?
It's hard to say.
It's hard to say, okay. Yeah. It's kind of my guess of it, just looking at the numbers.
Although I did, when we get the observations later, I imaged it 4 days ago.
Okay.
With the moon 15 degrees away, and it came up quite nice.
Oh, that's good. So we'll see. Again, all the good standard suggestions, DSLR on a tripod. Yeah, this is basic. Don't forget, these things are big, wide sky things. Looking through a telescope is not the greatest thing. If you're going to use a telescope, make a nice rich field one, because that's going to be your best way to do it. I'll leave this. This is one thing I hate, it's somebody reading the stuff off the screen. Yeah, I can read, bozo, so I'll let you guys read it. Okay. There we have comet Pan-STARRS, and, well, we'll see Paul's observations, with some excellent suggestions, at least I think they're excellent, for how to come up with guesstimates. Because remember, you're going to be fighting two things here. You're going to be fighting the intrinsic brightness of the sky, really so now because it's before dawn, so you're going to have to try to balance that off. Make a big, long exposure, you're going to wash out the sky. Make a short exposure, you're just not going to get much comet. Maybe that's where the stacking with a digital camera might come in handy. I don't really know. Well, I guess we'll have to see. And then, again, nice dark place with a low view to the, nice view to the southeast. So that's a little problematic for most of us here, finding a nice spot that will do. Finding nice clear views to the southeast in the Ottawa area is not the easiest thing in creation. Even Paul, I guess, is a little disadvantaged with that one. If anybody has a nice place where he's chopped down all the trees to the southeast that's dark, no, I shouldn't mention our president, but I suppose we could suggest that he open his doors to the entire RASC, but that's probably not sensible. I understand the electric fence will be installed later this week. Yeah, the tasers and the electric fence, right? Hey, it's Comet Gary! Yeah, anyway. Yeah, that's the guy flying over the fence. So, what can I tell you, folks? Oh yes, Hale Bopp in '97. Certainly much nicer, a comet of the last century. Sorry, guys. ISON, no matter what happens, is probably not going to look like this.
Really?
That's my best guess. You heard it here first. I'd love to be absolutely and totally wrong, but we'll just have to see. Of course, it will be cloudy the entire month of December. I am positive it will be cloudy.
Tim, I had a question.
Yes.
Regarding the Roche limit earlier,
Yep.
is that what applies to the moon Phobos? Is that the reason why it's demised?
Partly. Phobos is unstable. The orbit is actually shrinking, and part of that is losing energy from tidal distortions. It actually is losing energy heavily from being simply bent and stretched and kneaded.
It's going to crash in, I think, in about 6,000 years. Is that right?
I read 60,000, but hey, who cares?
Yeah.
Who knows? There's always some good science fiction stories written about how people are farming on the debris from Phobos and all that stuff. So, because it is carbonaceous. I don't know. We'll see. But yeah, a lot of times the satellites do decay because of the tidal interactions. There's so much energy loss in the process that the orbit decays terribly. Anybody else? Hello.
Yeah, Tim, it's worthwhile to point out
Yep.
that the magnitude calculations of the comet only apply to the head of the comet.
Yeah. Good point.
If you have a long, extensive tail,
can
the
repeat
integrated
that.
light of all of that
Yes, I will.
is more than the head. So it's mostly the
Excellent point. Thanks, Glenn.
that can make it more spectacular.
As Glenn LeDrew is pointing out, the magnitude calculations apply to the nucleus, and it doesn't take the tail into consideration. So, again, all these things are wet fingers, back of the envelope. There's absolutely no substitute for looking at it yourself. That do it for you, Glenn?
Good enough.
Okay, excellent. All right, folks, good luck. Clear skies. Sacrifice as many chickens as necessary to get a clear sky. It's the best I can think of. And cross your fingers and do not make any reference to imaging ISON or the Murphy gods will kill us all. Okay?
Thank you. Well, thanks, Tim. That's an excellent summary. And for those of you that do want to try to take your first stab at astrophotography, one of the last points on that slide was to try to get out before the comet comes. Yeah, you don't want to be, especially if it's December and it's like -5 or -10, you don't want to be starting to learn how to operate change your camera settings in the dark, in the cold. Trust me, I've been there, done that. You don't want to do that. So if you want to try to grab a picture of it, practice in the early morning sky. Get out there, when we do get some clear nights before then, and just shoot the Pleiades is a nice target. You can get up there and just practice with that. So yeah, give it a try there before the big show. All right, thanks again, Tim. That was an excellent summary. Next up on deck, Jonathan is going to talk about a universe from nothing. Poof. Just like that.
Not quite.
Not quite, eh? Thanks.
Well, it's going to be interesting to see the images that you folks are going to get on that comet over the next couple of meetings. But now this actually is not just a book report, but also a lecture report. A very interesting new book has just recently come on the market, and as you can see from the cover of the book, it's a New York Times bestseller, and it's good to see some good hardcore astrophysics hitting the bestseller lists around the world. And this one is especially interesting because Professor Lawrence M. Krauss, who is a graduate of Carleton University, is the author. And very interestingly, I didn't know that he was coming to Ottawa to give a major lecture a couple of months ago. Now, I found out basically by accident because the invitation was on one of the pages of the Carleton alumni newsletter. Now, I'm not one of the science alumni, but two of my kids are Carleton University alumni, so they get the magazine, but they're so busy in their careers now, they don't read it. So the old man reads it. There are advantages to being retired. And there was an invitation to come and hear Lawrence give the Discovery Lecture at Carleton University. So I don't know if my conscience should bother me or not. I thought there was going to be a little reception afterwards and so on. So I thought I'd kind of break into the party and go without an invitation. But it turned out to be a very worthwhile evening. By the way, did any of you here get to the Discovery Lecture at Carleton University? You did. Excellent. Only one. That's disappointing. Only one. Well, one thing I would like to suggest is that when we have a world-class speaker like that coming here to Ottawa, especially, that he's got Ottawa connections, it's too bad that a group like ours couldn't liaise better with Carleton University so that when they get an astrophysicist coming in like that maybe they could extend the invitation to us and we'll return the favor. We'll let them know about all the special events that we have and we'll invite Carleton University to our events. So I hope we can do that. So as I say, I found out by accident that he was going to be there, and they actually packed out the auditorium. I was quite surprised they did not have to advertise it. Maybe that's why they didn't want to advertise it. The auditorium was packed. They had to go right into overflow, closed circuit television. So a lot of people are interested in this subject. Now, this is a very interesting question. Why is there something rather than nothing? A few years ago, Stephen Hawking himself said that question bothered him more almost than anything else in astronomy and cosmology. And he could give no answer to it. Because how is it that we have something? Where did all of this complicated universe come from? Well, here, Professor Krauss writes a book on the latest information from it. Very interesting. Now, whether or not you believe in his hypothesis or not doesn't matter. It's worthwhile hearing what some of the top minds in the world actually think about how this universe got here. So we went to the lecture, and it was very informative. We would have loved to have had you folks there because he gave a beautiful history of astronomy, the amazing discoveries, what the ancients knew about astronomy, how little they knew, and how some of the greatest discoveries have been in the last 100 years, especially with the making of the large telescopes. So it was a very good description of the history, and I was very surprised, too, that he would feature the fact that how much we know about the universe and yet how little we know about the universe. In fact, every time they get a new fact about the universe and it answers one question, 3 or 4 more questions come up in its place. And we find ourselves deeper and deeper in the dark. So the book is a very enjoyable read. It is made for general audience, although there are some technical parts to it. But he goes through some of the different theories and ideas on how we got here and what scientists are saying it and what theologians are saying about it as well. So even though he himself is not a theologian, he is an astrophysicist. And he mentions quite often in the book that if this is so, then such and such will happen. If that is so, then such and such a thing will happen. And then he'll mention something in outer space and say, well, we believe that this is what is happening. I really appreciated that because, we shouldn't be too quick from our small vantage point here on Earth to make definitive statements about we know exactly what's going on in that comet, we know exactly what's going on in this star cloud in outer space, like Tim Cole is a good example of showing how little we know. I like the way Tim presented that, how little we know. Here, comet ice, and this is a next-door neighbor, and how little we know about what's going to happen. I'm looking forward to seeing what's going to happen here. So Professor Krauss mentioned the fact that we should be very careful about whether or not we are going to be definite about what we actually know or what is just hypothesis or theory. So this was a very interesting lecture. Now, after the lecture, I had a couple of questions that I wanted to talk to him, and fortunately, there was a good reception, and I took the time to go there and have a little talk with the professor. There's a long lineup of people wanting to sign his book and so on. And I hope every starving student at Carleton University was there, because they had a lovely buffet table with lots of food. So I hope the students loaded up on it. But more important than that, when I got to talk to Professor Krause, now, some of you might think, if you know my personal philosophy on science and theology, you might say that I would be a little bit hesitant talking to Lawrence Krause, because he doesn't have too much time to give to creationists like myself. And but as I have found in talking to people, successful people of high intelligence, that they are not challenged by people who disagree with them. They do not fight or argue with people who disagree with them. And so when I told him that I was a biblical creationist, he didn't argue with me or fight with me or anything. He was quite happy. He smiled and was quite happy to discuss the differences. And so I said, but I do have a question for you, Professor, on your book. There is an apparent contradiction in your book. Well, he looked at me and said, "You mean only one?" I didn't know what to say to that. He caught me off guard. All I could say was, "God bless you, Professor," not thinking that he probably doesn't believe in God. But we got in there. He then stopped me and said, "You know, you think I'm an atheist, but I'm not an atheist." And I was quite surprised to hear that. He says, "Actually, I'm an agnostic. I leave that question open." He says, "Now, I don't have any use for your God, but I leave the question open." So I was quite surprised to hear that. In fact, what made me so surprised, notice the afterword by Richard Dawkins himself, a very vitriolic atheist who has said some quite nasty things about people who believe in God. But nevertheless, that is really not the way that Krause says that we should be discussing it. For science and faith do not have to argue with one another. No one should be forced to believe in anything. You can come to your own conclusion as to how the universe got here, and so can I. Now, so I asked Professor Krause, I said, "Now, you believe that our universe came from a spontaneous quantum fluctuation out of nothing. However, you also believe in the multiverse theory." Now, most of you know what the multiverse theory is, that beyond our view, it's completely hypothetical, there's no evidence for it, but beyond our view, beyond the Hubble ultrafield view of the universe, there are endless numbers of universes that stretch on forever and ever. So I mentioned to the professor that if you believe in the multiverse theory, then nothing has never existed. So we don't have a universe from nothing. According to your book, something has always existed. And very magnanimously, he said, "You're absolutely right." He says, that's right. He says, "There has never been nothing." He said, "But the only thing that I am saying is that our universe, as a separate island universe, came into existence by a quantum fluctuation that we cannot understand." So he admitted that it's just an hypothesis at this present time. And as far as the multiverse theory is concerned, it's something that is worth discussing and to see if possibly there is any evidence of such a thing. So we had a very good discussion back and forth, and we ended our discussion very amicably. We shook hands, and we agreed to disagree agreeably. And I'm looking forward to possibly seeing him again. Now, being the fact that Professor Krause is a graduate of Carleton University, and the fact that he got his reputation in the United States, he is quite likely to come back to town. And it would be good if anyone hears of him coming back into town. He'd be an excellent guest speaker at one of our events. And that's something for the administration of the Royal Astronomical Society to consider. But all in all, it was a very enjoyable evening. We had different points of view. The professor is a very good teacher. And if any of you hear that Carleton is doing another good astrophysical lecture, it would be good to let us know so that we can go in and hear this special event. Apparently they do it every year. It's called the Discovery Lecture, and it was a very enjoyable evening. Now, is there any time for any questions? Are there any questions on that right now?
Yeah, we're tight.
Okay, we're tight? Okay, then I'll be glad to discuss it with you after in the meeting there, and I'd be glad to hear your theories too, whether you agree with me or not. Thank you.
Thank you, Jonathan. All right. Yeah, we are running a little tight tonight. We have lots to show you tonight. Okay, Al, I know you're here. What's happening in the world or in the universe?
Thank you. Good evening. I've got a few interesting astronomy news items for you tonight. So let's get started here. First one is on black hole mergers. And this is an interesting topic. Astronomers think there are mega black holes at the center of most galaxies from the observational data that they have. And astronomers also believe, based on the relativity theory that and the mechanics of galaxy mergers, when two galaxies collide, it's likely that their black holes will spiral in towards each other and eventually merge into one larger black hole. And this is one of the theories that might describe how these huge billion solar mass black holes accrete in the center of these galaxies. So there's been an announcement by a team from the Parkes Radio Observatory in Australia that they've put an upper limit on the rate that this could be happening in the universe, which is really a surprise because I didn't know anyone was able to detect this with any sort of accuracy. Apparently what they've done is they've been timing pulsars in different areas of the sky. And these are millisecond pulsars, which are neutron stars orbiting or rotating at kilohertz rates, thousands of times per second. These stars are made of neutrons. They spray out radio waves across the universe, and the radio telescopes can measure these timings to really high precision, tenths of a microsecond. Gravitational waves from two merging black holes would emit outwards from the black holes at the rate that they orbit each other. And this would cause the pulsars act as clocks, and this would cause the pulses to speed up a little bit and then slow down as the black hole gravity waves stretch and compress space-time. So we actually have radio telescopes. If we can measure with enough precision the rate of these pulses coming from different portions of the sky, we can actually see any of these mergers happening in the nearby universe. And depending on the mass of the black holes and the frequency that this happens, we should be able to detect this. Now, the signal that they expect is like one cycle per year. So that's the rate of these two black holes orbiting each other. So you should be able to detect a shifting of the frequency in these pulsar signals from all different directions of the sky, which gets kind of a nice measurement of gets rid of atmospheric effects and solar system effects because you're measuring in all different directions. And the pulses would arrive, say, 20 nanoseconds early in July and 20 nanoseconds late in January. So it's a bit of a precise measurement to make when you're only timing them to a tenth of a microsecond. But because you've got so many of them, you can average out any errors and you can actually get to this level. And so this is actually a non-discovery that the astronomers have announced. They have not detected any gravitational waves. But this puts an upper limit. It actually limits the rate that these mergers could be happening, and it cuts out a lot of the theories of how these black holes might be growing. So interesting times. They've got about 20 years worth of timing data now, and they expect over the next 10 years that they should be able to detect these gravitational waves from mergers. So very interesting theoretical and physical study, very carefully done. This is an interesting one. Someone's detected a comet fragment in Egypt. Very rare because comets typically do not survive their interactions with planets, and they're very fragile things. The discovery is associated with a mysterious black pebble that was found years earlier by an Egyptian geologist in the Sahara Desert. In the desert in Libya, there's about a 6,000 square kilometer expanse of yellow silica glass scattered throughout the Sahara Desert. And in the middle of this, they found a black pebble, which seemed oddly out of place. What they did was they did isotopic and chemical analyses on this pebble. It's a amorphous carbon pebble, very hard. It's got micro diamonds in it, and they believe that it comes from a comet because the isotopic ratios don't match meteorites, and they seem more along the lines of dust that's been captured in the upper atmosphere from meteor shower or from showers, which could be originating from comets. Interestingly, this patch of glass was the blast wave melted the desert basically and made this yellow glass in the desert about 28 million years ago. As the comet entered the atmosphere, it heated up the sand beneath it to a temperature of about 2,000 Celsius. A magnificent specimen of this glass, polished by ancient jewelers, is found in Tutankhamun's brooch amongst the burial items with a striking yellow-brown scarab. The researchers have named the diamond-bearing pebble Hypatia in honor of the first well-known female mathematician, astronomer, and philosopher Hypatia of Alexandria. So an interesting discovery and very rare. My final item. This is interesting in that the star Fomalhaut has been recently discovered to be a wide triple star. Typically, multiple stars are very close together in the sky. You can see them in a single, telescope viewpoint. Well, this has been noticed through proper motion surveys from the Hipparcos satellite and measuring parallax of satellites of stars as well. The interesting thing about it, there's about 5.5 degrees between Fomalhaut and this newly discovered star, which is a huge angular separation on the sky for a triple. They appear this far apart because Fomalhaut is relatively close to the Earth as stars go, only 25 light years away. Fomalhaut A, the primary, is a very massive star, about twice the mass of the Sun. It can exert enough gravity to keep this tiny star, bound to it. The Fomalhaut C star is a red dwarf, a very common type of small star, 158,000 times farther away from Fomalhaut than the Earth is from the Sun. Fomalhaut A is a very well-studied bright star. It's the 18th brightest star visible in our night sky in the south, and one of only a few stars with both a directly imaged exoplanet and a dusty debris disk around it. Despite being such a well-studied system, it was only recently confirmed that Fomalhaut was a binary star. You can see where these neighbors are. Here's Fomalhaut, it's B, and here's the C neighbor. You can see it's really, really well separated. Astronomers have been puzzled why the exoplanet that's been imaged around Fomalhaut is in such an eccentric orbit. It's possible that the gravitational influence of these other stars may be causing this eccentricity in the planet's orbit. Also, the debris disk has been gravitationally perturbed by something, and this could be an explanation for it. Fomalhaut B, the one down here, is an orange dwarf star, somewhere in between the size of A and C. Because it's so far away, a planet, if it were orbiting Fomalhaut C, the newly discovered one, if you were standing on a planet orbiting that star and looking back at Fomalhaut A, it would be about the same brightness as Venus in our night sky. So, quite bright, but you wouldn't recognize it as a stellar partner unless you were really careful in your calculations. The age of this star system is about 440 million years, roughly a tenth the age of our solar system. So I just thought that was an interesting discovery, and you can probably all go and look for that if you want to to see it. It should be relatively easy to see. So thank you. That's all the news for this evening.
Right.
And now, changing hats, as past president of the Ottawa RASC, it is my solemn duty to also become chair of the nominating committee for the club representatives for the elections coming up in our annual general meeting next month, December 6th. So I have to put together a slate of nominees and present it to the members. So here we have basically elections every year, but typically members sit for 2 years at a term, so many of these members are being re-elected. We do have a treasurer position to fill and also a meeting chair position to fill. So Gary Boyle is going to stay as president. Gordon Webster is going to stay as vice president. Chris Tarrant is going to stay as secretary. Thank you all. We have 2 volunteers for treasurer this year, so we're going to get to have an election. Oscar Echeverry and David Parfait. And perhaps they'll address you at the election next month. Our councillors, Yves Demare, Carmen Rush, and Stephen Norris are staying on, as well as our national council reps. And I'll stay on as past president. I don't have much option there. So, just to let you know, is it in the next slide? The details? Yes, okay, good. So nominations may be submitted by any member for any position in good standing. Nominations must be supported by 2 members and sent to our secretary, Chris Tarrant, right here, by 8 p.m. on December the 1st for the elections on December the 6th. And as you notice, we are still looking for someone to volunteer to take over Paul's position. We also have a set of appointed positions that help out with the council's tasks. And you can see there's quite a good crew of volunteers here. We're always looking for help, though. I especially could use some help with the telescope loan library. If anybody's interested in working with telescopes and helping them come back to use or getting them out to members, I would really like to talk to you. So please approach me at any time. Okay? Thank you.
Thank you, Al. All right, just before break time, a couple of short pieces for you. We have the Paul Commission Observer of the Year award that we're eager to give out. So if you would like to be considered for that, please submit your images, or if you know somebody that should be considered for that, let us know, and we'll bug them for their observations there. And we need to hear from you by November the 13th in order to get things ready and to grant the award there. So please don't be shy. I know I've seen a lot of good imagery this year, and from some newcomers as well there. So please submit your images to Chris or myself, and that would be much appreciated. And for the annual dinner, just a reminder that tickets will be on sale at the break. Had a little change in plan there. Is Brian kicking around there? There you are. We've had a change in our speaker there, and I'm just wondering, Brian, this is very fresh news to me. Would you like to say just a couple of things about the lady that will be our guest speaker?
What do you mean a change in our speaker?
Sorry?
What, you said a change in our speaker?
Yes.
Change from what we discussed earlier on?
Yes.
That was nothing definite.
Yes, I know. I thought it was, but
okay.
yeah. But it would be good just to let folks know who will be addressing us at the dinner.
Yeah. Just to let you know, Dr. Judith Irwin, I just spoke with her today. I've been working very closely with Gordon Webster to find a speaker, and thanks to Al Scott, Sylvia Letourneau, and some others who were helping guide where we're going to look for a speaker, because we're doing this quite late in the process, and there was a reason for that we don't need to get into at all right now. But I talked to Judith today, and she and her husband are going to be coming down on the 15th. And I know she's a good speaker. I think some people have heard her before. and she's into a lot of radio type of astronomy. So this is her talk that she came up. She says, well, let's try this on for size. New glimpses of galaxy halos using the expanded very large array. All right, so she's at Queen's University. She's did her PhD there since 1998, so I think we can expect a really good presentation and a really good dinner. So if you've never come to one of the dinners, all the best people are there.
Absolutely, you got that right. Yeah, I like that. All right, and as I mentioned, Gordon will be available at the break for those of you that wish to purchase tickets for the dinner there. And just before the break, I've granted Eric 30 seconds. I will be timing you. There you go, sir.
Hello, everyone. So far, the broadcast is going very well. We're receiving feedback from people. So our first webcast tonight is successful. I'd like to mention quickly that we are only using, for those on the web, we're only using one audio channel tonight. That's normal. That'll be fixed in the future. Also, some people were complaining about the quality of the screen. We're having to use one camera, so for now we're working with that. In the future, I will be using two cameras with one focused on the screen so you can read the text better. And I thank you for coming and watching us tonight, and hope you enjoy tonight's broadcast. We've got a special presenter coming up, and we'll be back in about 15 minutes. So if you want to log off for now, come back in 10 minutes. Okay, thank you.
Okay. Well, thanks everybody for participating. We're going to do our observation reports. We've got some interesting imagery for you. And where's my? There it is. All right, Mr. Boyle. Mr. Boyle has some amazing shots for us tonight. Mr. Boyle. We're on national TV. Come on.
I was like an entrance, can I say?
There you go.
Welcome back. Okay, can I have the first slide, please? Well, no, with not having the observatory still set up in South Mountain, I'm processing some of the older images that I have. So this is the crater, what crater was it? It's like Herschel. Oh, yeah, Herschel. Crater Gary Boyle, yeah, crater Herschel. So I'm just doing a little bit of processing and trying to refine, but it still looks a little blurry here. It's better at home. Okay, next slide, please. In August, we had some fantastic lightning storms. In fact, that was the weather that next one of the star parties that we had at Carp. So really, and you can really actually see Sagittarius over here. It's just phenomenal, one cloud. It really didn't do much in lightning until it went over the St. Lawrence, and then it really started to crickle and crackle. It was very quiet too, so just for nice striations. But then the piece of resistance is the next slide. Just could not believe that one.
That's beautiful.
Thanks. Thank you, thank you. Thank you, Mother Nature. Thank you, Mother Nature.
Gary, how long were the exposures?
Well, really, the trick of it being in the country is very, very simple. I'm giving all my tricks away. See, in the city, if you try to keep your shutter open any length of time, you have light pollution. So just keep it at ISO 100. Keep the shutter open until something flashes, and then close it. So this is probably a 1 minute shot until something registered, and then I close the image. Yeah, but focus is the key ingredient. Thanks. Next slide.
No. Say something.
Oh yeah, sorry. And back in August too, the week after this, we had the Perseid meteor shower. Did anyone get to see any Perseids? Well, I finally got to photograph one Perseid, and here it is. Amazing, even clouds, I still got the one Perseid. Great. Thanks, Chris.
Point source when they were in the corner.
Yeah, I did. And a few weeks ago, this is the moon and Venus setting just down the street with the barn, with the silos over here. So just nice, beautiful sky color, and really enjoying country skies. So I believe that is it. Until next month, thanks, folks. See you later.
Nice work, Gary. That's excellent.
Frank?
All right. Frank, where are you, Frank? I know you're here because I talked to you today.
Other way.
Oh, there you are. There you go.
Right, so this is a 6-day-old moon. You're looking at Serenitatum here. And I thought there were some rather interesting features on this that I noticed that on the day that I looked at it. You can see at the top you've got a couple of obvious craters there. One's the Aristoteles crater, which is lava filled. It used to have a lot of internal structure, but it was all flooded by magma. So of course now it's plain more than a crater. And if you look in the inside, Eudoxus has a bit which is just underneath. This is the second top one. It's about 70 kilometers away from it. And this has central peaking, although you won't see the peaking because of the way that the shadow went. An interesting feature here in Serenitatis is not just the wrinkle ridges around the sea area, but it's also that you have some interesting craters nearby. So I'm not exactly sure where it is, but it's around here. This region here. And one of those craters, I wasn't exactly sure which one it was, but it's around this area here. One of those craters is Littrow, and near to it, so I believe it's around here. Littrow's around here, and you have Clerk here, and it's around this region. I think that the Apollo 17 mission landed in 72. So when Apollo 17 landed, of course, that's the last moon mission. It's interesting to think that if they had set up some kind of light signal, you could have been able to see the signal possibly from that area, depending on how they would have made it. So it's certainly an interesting feature, but it's also nice looking for the actual moon landing locations, especially on a clear 14-inch Schmidt-Cassegrain like they have at the Carleton University scope. So next slide, please.
Oh, before we go to that one,
yeah.
I wanted to point out what really strikes me in this image is the very obvious different coloration in the lava in Serenitatis and Tranquillitatis. You know, north we've got a brownish tinge. In the south we've got a fairly greenish color, which also leaks over into the left side of Tranquillitatis.
Yeah. So you're saying it's a slightly different formation structure?
Yeah, this entire lava flow here has got a greenish tinge. Here it's a bit more brownish reddish, and you see even a bit of the greenish tinge extending up on this side of the ocean, if you will. It's the kind of thing you can subtly see in a telescope, but I don't see many pictures that show the color difference quite as obvious as seen here.
Do you have an idea why that is?
Just different composition of the magma.
Right. So that's excellent. Thank you. So okay. So okay. Well, it's inverted. Sorry. You can see here it's the same as what Boyle showed you just a minute ago. There's Moon and Venus, but unfortunately there's no farm. So next slide, please. So this is the moon just early in the morning. I just thought it was a nice picture, so I just decided to post it there because you can see the blue hue and the cratering at the bottom. Next slide, please. And this is just a lead up to another picture I took at the NRC because I went to a workshop there a week ago, and at the NRC they have a really impressive area of experimentation that they use for engineering and aerospace. So what they do is they use this giant turbine structure on the right here, and they use that to test different conditions like cold conditions. And they want to see how, I'm not exactly sure which application they use this for, but it's for, but they can see how the temperature and would affect aircraft or whatnot in certain areas. So you can see the moon just at the top left there, and it's a bit of artistic license because it looks a bit like an Earth to the Moon image, but just thought it was interesting to show. So, okay, thank you.
Frank, can I have my pointer back? Frank, I think you stole my pointer. Did you steal my pointer?
Oh, I did, yeah.
Whose pointer? What are you going to do with these guys?
Can I steal it?
No, you want to steal it. Okay, I'll let Brian steal
Thanks.
it.
Moon and Venus. I just thought it was a nice shot.
Nice house.
Yes. If you go to the next one, please. Yes, flying there. And you know what? Of course. I took one shot, and then I thought, oh, and it wouldn't recycle fast enough. About a second later, those geese flew right across the moon. So what I need you to do is close your eyes and imagine. Move those geese across the moon. Is that a fabulous shot, or is that a fabulous shot? You can have that back.
Photoshop, Brian.
I was going to say I have one word, Photoshop. Nice one, Brian. All right. Oh, wait, Brian. You missed one. Brian.
Yeah, I see it.
Yeah?
I was goose, didn't get it. This one from the cottage.
Okay, there. One from the cottage. No faces in this one, right, Brian? Okay. All right. Where are we at? Oscar, there you are.
No farm.
No farm.
No farm in this one.
No
No,
geese.
no farms in deep space, unfortunately. Don't know exactly what we'd grow out there anyway. So yeah, I bet most people here are familiar with this one. This is M27, the Dumbbell Nebula. It's a planetary nebula in Vulpecula. So it's about 1,250 light years away. I took this one with a shiny new Canon 60DA that I picked up last month or the month before, I forget now, through my 8-inch Newtonian reflector at f6. It's about a 45 minutes worth of subframes in any event. Pointer?
Was there? Did Brian steal it?
There it is. Lasers in the middle? Yeah, okay.
Yeah.
Which one do I hit for next? This one?
Yeah.
All right. Look a little better on my monitor. Anyways, this is M33, the Triangulum Galaxy. There's also a whole series of other NGC objects in here. The most obvious ones are NGC 604. Pardon my shaking there. 604. Too much coffee today. And what was the other one on there that I had marked? NGC 595, which are both H2 star-forming regions. The interesting bit about NGC 604 there is that it's about 40 times larger than the Orion Nebula. It's sort of the same composition or similar in any event. So this one's about a 4.5 hour image composed of 5 and 10 minute subframes. This one's through my 80 millimeter apochromatic refractor with the 60DA as well. Cool, that's it.
Excellent. Those are beautiful, Oscar. Excellent. All right. There we are. Oh, the names are all cut up. Yeah, Rajesh, I haven't seen you there. I know you're here, but there you are. Hi.
Good evening, everyone. So earlier in September, actually, I did get a chance to go to a farm. This is at Bootland Farm. I took a picture of the Milky Way galaxy as shown here. And yeah, I would have presented this last semester if it wasn't for those pesky midterms, right? So yeah, and yeah, this is actually taken last month in at the Carp Star Party. Again, I tried to replicate the photo with the Milky Way galaxy, and I actually got a meteor in there. So yeah, just a streak of meteor. And I thought this was a pretty cool photo. I also rented out a fisheye lens to capture a greater field for that photo. And finally, a couple of weeks ago, I managed to capture M42. So this is the nebula in Orion, and it was actually my first stacked image. I'm a little inexperienced with stacking images, but I thought it turned out pretty well. So yeah.
What camera were you using?
Thank you, guys. I was using a Nikon D7000 for this photo. All right. Thank you very much.
Excellent. Thank you. All right. Bob, where are you, Bob? There you are.
This is the Heart and Soul nebulas. I think you can see which one's called the Heart. They are that position in the sky, so I'm missing the middle picture. It'll come when the sky's clear. If you notice, there is a slight difference in the color of the two of them. You know, I guess it's a judgment, but I would say this one is nicer than this one, and that's because this one has hydrogen alpha data in it. which since the red is mostly hydrogen alpha emission lights, the picture will look nicer. Okay, next one. I'm assuming this is the separate. These are the individual images. This is the Sol Nebula. And the next one. And obviously, the Heart Nebula. And that.
What constellation are we in there, Bob? What constellation are we in there?
This is around. It circles around Polaris. I actually don't. Just below Cassiopeia.
Yeah, just a little above the double cluster.
Yeah, actually, I have an image of the double cluster that's coming soon too. I was imaging that section of the sky. Okay, next one. And I got a new camera, so it takes pictures of big things. So this is the obligatory picture of M31, which takes up like half the sky. Okay, thank you.
Bob.
Sorry, one more thing. Hi, Mike. How you doing?
There we go. Say hi to him.
Hi, Mike. How you doing?
Mike Wirth's in Baja.
No?
He's right there presenting.
Oh. Oh. Hi, Mike. Yes? And we can roll? Are we? Yeah, okay. So yes, Mike Wirth's our long-distance associate for the Ottawa RASC Centre, who's residing in Baja, has graciously sent us some really nice pictures of that one is of pan-stars earlier in this year in March, taken down from his very warm and sunny locale. I know it was rather cold here in March when we were looking at pan-stars, so nice image there, Mike. Next one there. This one I love. This was awesome, Mike. This was taken through his 18-inch Star Master. I believe he too was playing with a new camera when he took this very high-speed camera, allowing very, very short duration images to be taken. And I tell you, that's in terms of the sharpness and the detail I'm seeing on Saturn. I think that's one of the best ground-based images of Saturn that I've seen in a long, long time. So nice work there, Mike. Thank you. Thank you for sending. All right. Thanks again. Oh, me, yes, that's right. I've got a couple for you here. It was interesting that Brajesh mentioned fisheye lens. There's something I want to draw your attention to, which I just gave a course in astrophotography down at the School of Photographic Arts. And one of my students there showed me a piece of equipment that he had just acquired there. And what it was an 8mm fisheye lens made by Bauer. And he had shown me some shots that he had taken with it, and I was quite impressed with it. So I made a few inquiries there and found out that Henry's was selling these. So if you, again, if for those folks that have never done any astrophotography but have thought about it, this is a great way to get into it. This camera, or this lens, and it's available for most major brands, Nikon, Canon, Pentax, etc., provides a 180-degree field of view. This was taken from my place there basically in my backyard there, and you can see the span of the Milky Way. You can see the Pleiades just rising in the east there, and the summer triangle there. It's a very wide field. In fact, that gives you the dimensions of what this lens is capable of on an APS-C class sensor, as you would find in most DSLRs. Very sharp. The coatings look great on it, and what I found out was even more impressive. It's $300. So for those of you that have bought lenses before, you know that's a bargain. And I'm thinking this is going to be a really fun lens to play with when we're looking at things like the Perseid meteors, or if we have a large display of northern lights, and perhaps if Tim is wrong and Comet ISON puts on a show, that may be a useful lens for it as well. But interesting to experiment with. Fully manual lens there, and does a good shot. That was, by the way, a single exposure using that particular lens of about 2 minutes there, and it pulled in a lot of detail. So
it's f3.5.
F3.5, yeah. F3.5 when it's fully open there, so it's reasonably fast and seems to give nice coverage right to the edge of the field there. There's not too much distortion in the stars. I was expecting there to be a lot more there, but it seems to be behaving quite well there. So $300, it's a steal,
And remember, Comet ISON is coming. Right, so there we go. Speaking of ISON, okay, so I did grab that shot of ISON 4 nights ago. That was my first attempt at ISON, and it's been cloudy. It's been cloudy ever since there. But this is one Tim, especially with some of the magnitude projections you were looking at. So when I shot this image, the moon was still up, and it was about 24% illuminated, and only about 15 degrees away from the comet. So this was not a great sky to shoot with, but still the comet punched through quite nicely. I'm not sure what the magnitude was. I didn't have time to check it vis-a-vis the neighboring stars there, but there's about a degree of tail showing that already. Some of the other shots that I've seen on the net indicate something closer to about 2 degrees there. So I think, once the moon is out of the picture there, and we get a look at it before the sun becomes too prominent at the dawn light there, we'll see a fairly reasonable object there. And I think this would be something good for binoculars already at this point in time under a dark sky though. So we're crossing our fingers. And what I did with this is actually a stack of 17 2.5-minute exposures. But I collected a series of 40 exposures in the window of time that I had available. So the next thing I'll show you is actually a movie of this comet's motion over a span of 100 minutes. So Chris, if you can roll that for me. So the bottom line here is that it's coming. It's coming.
How far is it from us right now?
You can see us right into the dawn light there. One of my favorite times of the day.
How far is it from us right now?
It's just this side of Mars. So it did a close approach on Mars, and I haven't heard whether they were. I know initially they were going to try to target the comet with the rovers cameras there, but the government went on holiday there in the States for a while there, so I'm not sure if they managed to pull that one off there. But yes, it is now closer to us than Mars is, and headed in there. So 4 weeks to the sun.
Did you get some rotation on Mars there?
That's not Mars.
Well, that's not Mars.
No, that's just another star in the field. So anyway, so keeping our fingers crossed there. Hopefully I have something even better to show you next time around. Thank you. All right. Thanks a lot. Next up, Mr. Hamner. Talking about Grail. A lot of moon stuff tonight. That's excellent. There you go. Mitre?
You want your box back?
Oh, got it out of your way. Thank you.
Thank you.
Excellent.
All righty. Let's see if I can remember which button to push. Is it the big one in the middle?
For the laser.
For the laser? Okay, good enough. And just in case I don't like that one, then I'll use this one. There, okay. Okay, Chris, we're good. Now, I think most amateur astronomers enjoy observing the moon through their backyard telescopes. I know I certainly do. You may be curious about this particular image of the moon. It's unusual to say the least. It's likely a Photoshop fake. But I chose it tonight to emphasize my take-home message in this talk, which is this. The moon is not WYSIWYG. It's not what you see is what you get. There's more than meets the eye, more than meets the telescope-assisted eye when you're actually talking about the moon. What you observe visually only tells you about the surface, not what's underneath. So in the spirit of looking at the moon somewhat differently, as this image suggests, let us start looking at the moon somewhat differently. What would we see if instead of looking at the moon using light, we looked at it using gravity? Next one, please, Chris. Now, most people, when they think of gravity and the moon, picture this in their mind. Something along the lines of the hit song by The Police. Those of you old enough to remember what Sting did when he first started. You remember the song, Giant Steps Are What You Take, Walking on the Moon? But the geophysicists are very serious when it comes to gravity, as it's one of their major observational tools. Tool that they principally use to detect and study geological features hidden from sight, hidden underground. Next one, please. So in 2011, NASA launched an extraordinary gravity experiment to investigate the moon in high resolution. In typical physicist fashion, they had to come up with a catchy name for the experiment. They called it GRAIL. I think they were inspired by Monty Python. Gravity, Recovery and Interior Laboratory. More than a little opaque, if you ask me. I think that Monty Python got the better deal here. GRAIL comprised 2 satellites, each about the size of a fridge, nicknamed Ebb and Flow. And as they chased each other in orbit, I didn't make this up. As they chased each other in orbit around the moon, variations in the gravitational tug of different parts of the moon changed the distance between the 2 satellites. Geophysicists then used these changes, they were measuring them with microwaves, by the way, to make high-resolution maps of the moon's gravity. Next one, please. Now, this is a detailed artist's impression of what ebb and flow looked like in action with the Earth in the far distance. Next one, please. Now, NASA's mission description gives us a general introduction to what the GRAIL satellites are really recording. In other words, what the gravity values actually mean. Gravity measured over any point on the moon, actually measured over any point anywhere, is the product of the total lunar mass beneath that point, right the way down to the center of the lunar core. However, since the magnitude of gravity varies with distance, the deep lunar interior contributes a broad background signal. And most of the detailed variation in the gravity signal comes from the shallower parts of the moon, those parts that are actually closer to the GRAIL satellites. I'll say more about this in just a minute. Next one, please, Chris. Meanwhile, what do we mean by high-resolution maps of the moon's gravity? Well, here's an older gravity map of the moon. The whole moon, by the way, if you look carefully here, you'll see down here that, in fact, that's 360 degrees of longitude, and it's only the polar areas that have been chopped off. And this is a map made from the late 90s, obtained by the orbiting Prospector probe. And remember, it's a gravity map. So yellow is the general background gravity signature. The red colors indicate stronger gravity signatures, in other words, positive anomalies. And the blue colors indicate weaker gravity values, in other words, negative anomalies. I'll explain why in just a moment, but note 2 things. First, there are circular anomalies on this map, like here and here, here, all over the place. Some of them are concentric in form, and you've already guessed that these are large impact basins. I'll tell you which ones in just a minute. Secondly, there's a general north-south graininess to the image that tends to blur the details. So this is a low-resolution gravity map. Next one, please. Here's the equivalent map made by GRAIL in 2012, and I think you can easily see why this is such a high-resolution image. There's so much more detail here that's observable. And just so we can locate ourselves, this would be Imbrium. Over here, Serenitatis and Crisium. Down here, this would be the South Pole Aitken basin on the far side of the moon. And I think that'll do us for locations now. If we just switch back and forth, Chris, just so that people can see the difference between low resolution and high resolution. Go back to the high resolution, great. Quite a difference. Let's move on. So, what are the factors that determine the strength of gravity and whether we record positive or negative anomalies? We need to address this question to know what these maps actually mean. Isaac Newton in the 17th century demonstrated the critical role played by distance, but he also showed the primary role played by mass. Now, at high school, you all learned that mass is directly related to density, and rocks of different chemical composition have different densities. These near and far side maps, this is near side, that's far side. Just wait to be a little rung in here. These near and far side maps give you some idea of the broad variations in density outside of the major lunar mares, which are white in this image. They're blank essentially because they're filled with basalt and there isn't that much density variation within them. Next one, please. But density is not just a function of chemical composition in an environment like the moon. Billions of years of impacts have broken up the lunar surface into everything from boulders to dust, introducing pore spaces, or more technically, porosity. That decreases the density of the surface materials down to depths of several kilometers, thereby introducing further variation in the detailed gravity signature received by the orbiting GRAIL satellites. Next one, please. Now, like the Earth, the moon has a crust, a mantle, and a core, and each has a characteristic, though variable, thickness. This thickness variation leads to variable mass in each of these zones in the lunar interior, again introducing variation in the gravity signature detected by the Grail satellites. And again, this is a map of crustal thickness. There is the South Pole Aitken Basin. There's the Moscow Basin. These are on the far side. Here's Orientale for once on the not quite on the near side, and Crisium, and that of course is Imbrium and Serenitatis. Next one, please. Okay, now that we know what causes gravity to vary, can we now make a definitive gravity map of the moon? Well, yes and no. At least not yet. There's more we need to understand about making gravity maps first. Given that most of the detailed gravity signature comes from the near surface, we have to be very aware of the role of topography. And while we're on topography, there is Imbrium, there is Serenitatis, there's Crisium. Trying to think which one that one. Oh, that's Humorum over there, and that there is Nectaris. So this is obviously the near side. Suppose I record the gravity variation over an extensive flat plane. The map variations in gravity signature are going to reflect the factors we've just discussed: density, porosity, thickness, and depth below the surface of the rocks involved. But what if I now dump a mountain range, say the size and height of the Canadian Rockies, onto my plane and then remake my gravity map? That extra mass of the mountains that wasn't there the first time around, remember this is a mind model, okay, is going to add new gravity signatures depending on what the mountains were made of. Lighter rocks will tend to create negative gravity anomalies, and denser rocks will tend to form positive gravity anomalies. And such a map is referred to in the gravity world as a free air gravity anomaly map. In other words, that's the raw data that gets measured before any corrections are undertaken. Next one, please, Chris. Now, what if the geophysicist is trying to map geological features below the surface topography? She or he must first remove the effect of the topographic mass. In short, we transform the gravity to correspond to what we would see if the moon were smooth as a billiard ball. 1 second, Chris. So again, just so you know where you are, there's Imbrium, there's Humorum. I'm not quite sure exactly what that is there, but I believe that that is where Orientale is sitting. The result after processing is what's called a Bouguer gravity anomaly map, named for the man who came up with the method of doing it back in the 19th century. Now, I just want you to, they're off the top there, unfortunately, but Chris, can we flip back and forth here between the free air and the Bouguer? And the difference isn't enormous. The real difference is up here. And that was actually what I really wanted to use to illustrate. These images here are free air versus Bouguer. And I think you can see there's an enormous difference. This is exactly the same spot right there and there. Unfortunately, these were the smallest, lowest resolution maps on the entire Grail website, and I wanted to use them at this size. They don't work. But if you look at those, you can see that there is often a major difference between the free air and the Bouguer gravity maps. Next one, please, Chris. However, sometimes the free air gravity map is very useful, especially when comparing two areas of very different topography, such as the near and far sides of the moon seen here. And again, just quickly, that obviously is Imbrium, Serenitatis, Crisium, Humorum, and Nectaris. Notice the difference here between their Grail free air anomalies and how they emphasize the detailed topographic variations on the far side. Next one, please, Chris. In fact, as you see in this montage, Bouguer gravity maps may lose a great deal of potentially useful data, depending on how exactly they've been processed. It all depends on what it is you're trying to emphasize using the data. Okay, so my take-home message at this point is what? If someone shows you a gravity map of anything, including the moon, your first question has to be, what kind of gravity map is this? Because you cannot mix and match apples and oranges, especially when you're trying to make comparisons. Next one, please, Chris. So now we understand what basic gravity maps are. What do the Grail maps actually tell us about the moon? So here again is the detailed free air gravity anomaly map of the lunar far side. This here over here is the Moscow basin. That actually is Crisium, so it's not entirely the far side, it's just most of it. Large circular red anomalies, such as over here, are positive gravity anomalies that tell us that those impact basins are what is known as mascons, or mass concentrations. Something very dense lies at some relatively shallow depth beneath these impact basins. What is it? What is it that's so dense? Is it the lavas that are actually filling the basin? Is it the mass of a dense lunar, a dense impactor? Or is it the mass of a dense lunar material coming up from the mantle that rose towards the surface in response to the impact? I don't know. Note the large number of smaller, circular, negative gravity anomalies here in blue. And they represent relatively large impact craters. Why do they have negative gravity anomalies? Perhaps they're filled with fractured, crushed, and pulverized rock derived from the impact, hence relatively low in density. I can speculate, but I don't know. And finally, note that large concentric anomalies, like this one over here, comprised of a central positive gravity anomaly, surrounded by a ring of negative gravity anomaly, and then surrounded entirely by another ring of positive gravity anomaly. These appear to be mascons surrounded by an inner ring of impact ejecta, surrounded itself by an outer ring of something dense. But I can only speculate on what that latter might be, and I'm not going to do so. Next one, please, Chris. So let's now turn to the most powerful geophysical method for processing gravity in order to image hidden geological features, gravity gradients. If a gravity signature varies in 3 dimensions, then it's possible to make maps of the variation itself. This is done by quantifying the rate of change of the gravity values, either in the horizontal direction or in the vertical direction. The resulting gravity gradient map is no longer featuring gravity values, it's now featuring gradient values. These 3 views here of different faces of the moon show a background vertical gravity gradient value in green, and both red and positive red and blue negative linear gravity anomalies, some of which are arranged as concentric rings. You can see them here. If anyone wants to know what positive and negative gradients are, I can explain them later, but let's leave that to one side for the moment. What does all this mean? Next one, please, Chris. Here's a detailed look at the lunar far side. Note the South Pole Aitken Basin is down here. The circular concentric gravity gradient anomalies clearly relate to large craters and impact basins. I'm not going to get into the alternating positive and negative anomalies here. It really would be complicated. However, note the long linear blue negative anomalies. They're all over the place. You can see them up here. You can see them over here. There are some long ones. There are some short ones. These are interpreted to represent dikes of basalt, hundreds of kilometers long. They're vertical sheets of magma that rose from the interior of the moon early in its history, and these are much easier to understand. Why are they systematically blue, negative? That part is also a little complicated, but I can explain it if anyone's interested at the end of the talk. Next one, please, Chris. So let's go back now to the gravity gradient maps of the 3 faces of the moon, and we can see highlighted in these light patches that these long linear negative gravity anomalies are everywhere. And that is telling us that these hundreds of kilometer long, tens of kilometer wide mafic dikes of basalt magma are everywhere on the moon. And this is significant for us as amateur astronomers who observe the moon through our own telescopes. Next one, please, Chris. But hold on a minute here. If these giant dikes are everywhere on the moon, shouldn't we be able to see them with our telescopes? Here's an example from Earth. And there's no doubt about the presence of this magmatic dike here. I don't even need to point it out to you. Next one, please, Chris. But in this lunar example, and it's a big example, this is 30 degrees of longitude along here. Here you see a long blue linear dike, a mafic dike, and there are these little points here. It's quite obvious on this diagram here, but if we go over to the topography of exactly the same area, there are the dots indicating where that dike is in the gravity. There's nothing there in terms of surface expression. Next one, please, Chris, and we'll skip that one. There we go. The likely explanation for the visual absence of these very large magmatic dikes on the moon is quite simple. Either the surface of the moon has been heavily gardened by billions of years of impact cratering, thereby obliterating any surface topographic expression of these ancient dikes, or the dikes are deep-seated, and they never actually did rise into the shallow lunar crust. Of course, they never got to the surface. Remember that on Earth, it's the differential resistance to erosion agents such as ice, water, and wind that allows the topographical expression of similar magmatic dikes, on the planetary surface here. And of course, those erosional agents are absent on the moon. Next one, please, Chris. So finally, the Grail mission ended in December 2012. With the deliberate collision of the ebb and flow satellites into the lunar surface at a site now named in honor of astronaut Sally Ride. Last one, please. So here's my take-home message for you for this evening. Next time you're looking at the moon through your telescope, remember, the moon doesn't reveal all of her secrets. Thanks for listening.
Simon, come on up to the mic there.
Oh,
please. Thank you.
Yep. Question. I need to go over here to hear it.
So, what is the reference that is being used to measure the gravitational anomalies? Like, what is the zero reference?
Good question. Top of my head, I don't know. Chris.
Is this same technique useful when looking at Earth to find the meteor craters that we can't see through erosion?
That's going to be an interesting one. There was an identical experiment was done around the Earth using two satellites. They were both measuring sea level, and they were doing the detailed resolution of gravity mapping of the Earth. I haven't seen those maps, but they could be very useful. Depends. The chances of an impact actually being preserved at depth are low. These would have to be very large craters. Chicxulub would be an interesting one to look at, and I haven't seen the map.
I had a question. Neil Armstrong actually commented on mascons affecting his trajectory when he landed on the moon. I'd like to know, is mapping the gravity going to affect future missions where we navigate around the moon? Is this a significant part of that?
Yes. You may remember that, in fact, plate tectonics was discovered on the Earth because it was actually the American military were actually mapping the magnetic signature of the ocean floor in the Atlantic Ocean because they wanted to be absolutely sure that they knew exactly where they were and their compasses weren't being deviated. You can be sure that when they actually did this mapping here, it's not just because it's nice to know about the gravity map, it is going to have something to do with future missions as well.
Thank you. Super.
Thank you, Simon. Okay, we are definitely running a little, I didn't do that.
No, that's me.
That's you doing that. We are definitely running a bit late. So Jim Thompson has graciously agreed to postpone his talk on imaging or photography of the 1980s versus imaging in the 21st century until next month's meeting. So thank you, Jim. Sorry we couldn't get you on there tonight. Just in wrapping up our usual closing announcements, Estelle has got a very timely book for your consideration for this month, the Comet Sweeper. So Estelle is here, and we'll open the library for those that would like to have a peek there. And yes, just a further announcement there in 2 weeks' time, actually in 13 days' time, the museum here will be hosting this. We mentioned this last month. This is a talk on the Northern Lights. I think this is going to be quite interesting. From the myths that surrounded these features in antiquity to modern our modern understanding of them. The lecture is free, but the seating obviously is limited. It will occur right where you're sitting there. So if you're interested in coming to this, you will have to reserve a ticket, and you can pop up onto the website there to do that there. This sounds like it might be an interesting event there. So again, Thursday, November the 14th for that. All right. And again, Gordon, you'll be around for a bit still? There you, oh, there, you're really not kidding, way back in the corner. So Gordon will be around, so if you didn't get a chance to approach him and you want a ticket for the dinner, please see Gordon. And we have, oh, what's that? There we go. Just a bit there. In terms of parking, there's ample parking available at the Algonquin College near Salon D. There, if you haven't been there, there's a couple of big parking lots there. You can see we've labeled them there, number 8 and 9, with the salon itself indicated by the circled letter D there. So if you haven't been there before, there's no problem with parking, and I don't think you have to pay either, do you? All right.
The signs say you do, but it's not enforced.
It's not enforced. Okay. That's a good thing. We should get some of those signs here. Anyway, all right. And also to let you know that available at the dinner meeting and next month will be the 2014 RASC Observers Calendar. So we don't have them.
Our apologies.
We were hoping to have them today.
A month ago from national office, and they haven't come yet.
So yes, lost or hung up in shipping. Unfortunately, we were hoping to have them available for tonight. We will definitely have them available at the next month's meeting. Okay, so don't go out to somewhere else and buy an inferior product. You want the RASC calendar, definitely. All right. Estelle, as I mentioned, is here. Al is with us for a bit there as well afterwards. Art and Ann are out in the hall serving goodies. You can also talk to Art about membership info and cards. And the rest of the museum is closed as always. And we have our little gathering over at Kelsey's for those that are so inclined. And thank you, everybody, for coming out. We had 109 tonight, plus our extended audience. 88 now.
88 more.
Oh, we're up to 88. Oh, look at changing on the fly. This guy's wonderful. Where would I be without you, Chris? So yes, good turnout. Absolutely. So yeah, I'd say that was a success, Eric. Wonderful. Thank you again for everybody that contributed to materials for tonight's talks and their observations, and to the museum for hosting us as well. Try to get out there and check out ISON. We don't know how good it'll be, how long it'll be, but and how bad the weather will be. As a reminder as well, the next meeting is on December the 6th here, and it's also our semi-annual swap night. So if you have things that you want to get rid of, some good equipment, or if you're looking to buy Christmas presents for self, definitely come by next month there, and we will run the swap table from 7:30 to right up until the time of the meeting at 8 o'clock. So in the meantime, I wish you all clear skies, safe journey home, and we will see you all next month. Take care. Bye-bye.